being a group leader at the CCA, which my expertise is applying and developing machine learning methods and mostly deep learning in astrophysics applications. I hail from very different backgrounds, but my thesis is actually in astrophysics from Princeton. Then I went to Berkeley as a postdoc, went to Carnegie Mellon as a faculty, which is where I became interested in machine learning applications and development. And then I went from Carnegie Mellon to Berkeley again, and then to Flatiron Institute, which is a new institute funded 100% by Simons Foundation. And we do a lot of computational methods, applications, and developments to try to basically push forward the science in astrophysics. So that's a quick summary of what it is. Feel free to Google about it. What I'm going to talk about today is the work with Miles Kramer, Roy Xu from both Princeton students, Pablo Lemos from University of Sussex, now Jeffrey from ENS. I think they just moved also, both of them, and Peter Battaglia from DeepMind, which I think a lot of people probably heard of, and Alfredo Sanchez, David Spergel, and Kyle Kramer, who are astrophysicists and Kyle actually had just talked, I think. So without further ado, let me just show you what we've been talking about. Actually, before that, what we're trying to do here is that we're trying to push closer what a network can learn to some kind of understanding. So I'm not saying we get there already. We're just saying that right now we can use these symbolic regression methods, which I'll talk about what it is, to understand what some types of network is learning when it observes a bunch of data. And people should feel free to ask questions at any point, because I'm a big believer of asking questions during the talk, actually. So feel free, just raise your hand. I might not be able to see it, so if any of the coordinator and chairs can let me know if people have raised hands, please let me know, okay?
Okay.
All right. Yeah, thank you so much, Carton. So how do you understand a scene? This is a very funny way of starting a talk, because it's very linguistic style. But you look at a scene like this and you like to use one word to describe it. And very often you will describe it by thinking, okay, what is the right word to think about, and what is the position and situation that this thing is in? You parse it into physical objects and relations. And very often scientists do that anyway, but apparently a lot of people do that too, actually, not just scientists. And the reason about the objects and their interactions, how are they supported, attached, what are the things are going to fall? For people who are in the pandemic, I think a lot of us have very messy houses or apartments, and these things happen a lot. And it looks precarious, like things about to just collapse on each other. But what we usually do is that our brain runs this like intuitive physics engine in our head and say, okay, we have a bunch of stuff that's input on our left-hand side here. And then you run it through an intuitive physics engine to try to say from time t equals 0 to time equals to 1, 2, 3, 4, and to n, what's going to happen? Can we predict it? Would it fall, and which direction would it fall towards, right? And very often, we can use machine learning. Actually, in this case, it was really useful to use machine learning. And in this particular case, it's actually interaction network, which I'll talk about what it is. It's a type of graph network that describe a situation. And when you use this graph network, it will make it learn, basically, if I run a bunch of simulations like that, it will learn whether things will fall or not. So it realizes, oh, it's falling. And we also ask humans to decide whether they think it's going to fall with different scenario, different ways of putting the blocks together. And it turns out that actually humans and machines both do very well in predictions. And sometimes I was kind of surprised at how good both were doing. And you can also ask which direction it's going to fall, not just whether it will fall. And you can use different masses here to see how things would work. Same color, same masses here. And much more complex scenes like these, which I'm showing right here, where you have a force hitting from the left-hand side, and in trying to predict how many blocks of different colors will fall on the ground. And apparently the network can also predict very well. You can also infer the masses, because sometimes you might not know all the masses of the system. But by observing a bunch of the interactions, you can infer the unknown, which is very similar to what scientists do. Very often we want to infer some unknowns about the system, be it a conserved quantity like total energy, or it could be a mass of the planet. And then you can also predict how much fluid end up on both sides, either sides of these. So all these things are done actually with something called the graph network, when it watched over and over a bunch of these simulations, and it can start making very good predictions, as good as the humans actually. So as scientists, let me concentrate on a very specific case, which is basically a bunch of planets moving around, and say this is the sun and these are a bunch of the other planetary bodies, and it moves around for t equals 0 and t equals to 1. Can we predict what happened from watching only t equals to t equals 0, time equals t0? Can we predict what happened at time equals t1? So that's the question. Very often we observe these systems and we try to figure out what the rules are that govern them. So this is the Isaac Newton's apple tree, apparently in his manner. I don't know whether this is truly the famed apple tree, which he somehow discovered, the relationship between the heavenly bodies and the apples that fell on his head. But, how do we go from observing a bunch of bodies moving around to Newton's law in this case? We can observe the planets moving around, and can we figure it out, right? Basically what happened, what governs the motion of the planets. We can either work super hard and came up with it, or be super lucky. I don't know which way Newton actually went. And here we're trying to use something called symbolic regression. That is a part of this really huge family of expertise in genetic programming, evolutionary programming. But what it is, which I'm going to describe, is that we have a bunch of mathematical functions and variables, and we can form new equations. And once we form these new equations, we can check whether these new equations fit the observables. And then if it doesn't fit the observable, we move on to the next equation and find a better fit. And how we move to the next new equation and how do we actually do it fast is a very complex subject, and people have been working on it for a long time. It is basically a very gigantic search on equations and mathematical functions and variables, right? The possible issue is that it could have a very large space to search for the right equation. So now I gave you a tool, which is, okay, now you know that we can just run a really large sort of tree search, imagine. And you can find the right variables and right mathematical functions and to describe the system. But usually we don't do this because it's really expensive to do this large search so agnostically. So how does this all combine? We want to also understand, and we know that neural network is very good at doing these predictions, as I showed you earlier, either in predicting whether things will fall, which direction is falling into, what are the missing masses that we don't know about. All that neural network can do very well, and we were using graph network before. So a network that can work well in predictions, can we use it to help us sort of narrow down the space of the equations we need to search for? So you can go either way, right? One, you say observe system, my goal is to find an equation. But right now, as a human, it's going to be hard to search for the right equations just agnostically. Can I use neural network to help? And what I'm suggesting today is that we can use graph neural network that will help predict the dynamics first. And then we'll plug a chunk out of the graph network and interpret it. And you can look at it from a machine learning perspective, which is, interpretability and trying to interpret a network. But from a scientific perspective, it will say, oh, I have a system that I don't understand what the equation should be. Can I find the equations? And neural network is just helping us to sort of narrow down what are the important parts, because it does great predictions. So I hope I haven't lost anyone yet. I can pause here for a question if people like.
I just have a really quick question. What does the algorithm know a priori? Does it know, say, like, if you were trying to integrate with respect to time, does it know that, or is it figuring everything from first principles?
Yeah, so the neural network doesn't know very much. I mean, you don't tell it much at all, actually. You basically give, so in our case here, we'll give a bunch of bodies moving around, and in this case, it looks like a planetary system. And what are the prior information, or we can call it like the inductive bias in machine learning world, is that we know that these bodies are interacting with each other in ways that can be parsed into objects that have interactions with edges between them. So that's where the graph network comes in. And I will talk about what is a graph network in like next 2 slides, I think. And talking about and introducing this network that is extremely powerful in especially physical systems where you can parse into objects and interactions. So I can go into that. But yes, we don't really tell it anything other than what I just described. Any other questions? But this is a great question, by the way. It's like, what are the prior that you're assuming? Well, I guess the prior here would be, these are objects that interact with each other. And you can have choices for how to describe the graphical network, which I will describe a little bit more later. Other questions? Feel free, guys. It's better to interact, because otherwise Zoom talks can really put people to sleep. I mean, it does to me. All right, seems like going once, going twice, going thrice. All right, I'm going to go to the next part. I'm going to actually, you see my mouse moving a lot, but mostly because I want to check if people are like turning on this camera and trying to like talk and stuff like that. Okay, so next part. So now we like to do this in 2 steps. As I was saying earlier, we have a data set that's doing something. We want to predict its dynamics. So we model it with something called a graph neural net. And when we model this, there is a part where we want to minimize something. And very often we do a gradient descent. But when we're doing this training, we want to encourage low dimensionality representation in some of these parts. In this particular case, in the edge functions, which I'll describe what it is soon. And then we extract this particular chunk out and say, okay, let's interpret what the latent space is. And using symbolic regression and extracts and symbolic equation, which is what happened actually. This is the flow of the whole next part of the talk, but I just want to make sure that you guys get sort of sense what's happening. So let's concentrate on the predicting dynamics part first. And neural net is great at doing this, and we know that. We make predictions, this graph network, and we compare, we update the weights. And it's pretty, we've seen it before. It works with predicting directions it falls, whether it falls, predicting missing weights, missing masses that we don't know, predicting how many blocks fall off when you have like a very complex situation. This all works. So but just to show you what the graph network is. This is introducing one kind of graph neural net. There are many kinds, by the way. This isn't one particular kind. It's called interaction network. A graph is a natural way to represent the entities and the relations. Nodes here, which is the V1, V2, V3, correspond to entities, objects, and events. The edges correspond to the relationships, interactions, and transitions. So it could be many things. And we can do inference about the entities and the relations with respect to the graphical structure. So at the beginning of the pandemic, I was actually learning graph network for fun and trying to do it with COVID data set. So in those cases, you can actually model the nodes as different cities or different regions or counties. And the edges, in this case, I actually modeled it with, people's movement data. But there's a lot of noise actually in the whole thing. So it's very hard to model, it turns out. But graphs can capture many other situations too. Like molecules is obvious, you have hydrogen, oxygen, and you can have a very well-connected edge between the hydrogen and oxygen atom. You have the mass spring system where spring can be formed by many nodes where they interact with each other with these edges. While the mass here is interesting because you assume the mass doesn't get affected by the spring, you're really using a unidirectional edge pointing to the spring while the mass is not getting affected by the spring coming back down. For the n-body system, that's much easier. It's a fully connected graph because everyone's talking to everybody else. The rigid body system, the funny part is that the wall is the one that you assume is not getting moved by the bodies. So in this case, it will only have these unidirectional pointers, like these edges pointing out to the masses, while all the little bodies moving around are having like fully connected with each other. You can also use sentences and pass trees. You can also parse a sentence basically with nodes and edges, like the brown dog jumped, but like I'm not 100% sure I would necessarily model, all the NLP problems that you have with nodes and edges, because it's not the most obvious one, but you can do it. Image, and you can cut it into a scene graph and you can model the whole thing, be fully connected. So there are many possibilities here. And how does it work? So it's fairly simple. I mean, I shouldn't say fairly simple. It's quite simple. If you've seen it a few times, you have, for example, this ML system, which is really easy to describe. Nodes, nodes, nodes. You can also have like pointers that actually edges that points back to itself. And you have this U, which is a global variable, which could be, say, the total energy of the system or total angular momentum, something to describe the full thing. And if you like to, say, model a scene of party of people, they're moving around and how they interact with each other, this could be like the total number of people, like you here. And so how do we actually calculate all this stuff? You can compute the message function from node and here. So the node is VI right here. For the edges, you compute the message from the node and the edge attributes. Edge attributes could describe many things. Could be like, for this case, could be like the force constants, but we don't know what it is. It could just be a number that we don't know what it is, and we'll get updated and we'll get to know what it is. Or it could be something that you can give to the network if you know what it is. And then you have the sending node and the receiving node. So S for send, R for receiving, and then you have U being the global properties. And you have the node function, which you basically aggregate all the messages from all the different ones because you know which one points to you. And once you aggregate all the edges, you also have your node previous state, which is VI, this is VI plus, VI prime, which is current next state or current state, and U being the global properties. And then you would train to predict the node states from T0 to T1. So that's what's happening. I actually have a Twitter link that actually shows, how this interaction network is very powerful. Let me see if I can. Well, I'm going to show that later to you guys when maybe people just, can I click the link and send it to the people later? But yes, but all these come back to say graph network can do many things, including, representing deep set. It can be a relation network, it can be non-local neural network, it can be message passing neural network, just like simple things to do. So it's fairly powerful. And what we're concentrating here is that using such a powerful network that has strong inductive bias in this case, which is, things can be parsed into objects and relationships. And using that to help us get to an understanding what the system we're observing is doing. So each planet is a node. This is a case study. We're going to use the planetary interactions because something that astrophysicists can do fairly well. For any pairs of planets, there's an edge. So we create a fully connected graph. Each edge is a function of the two nodes, and the update on each node will depend on all the edges that acted upon it. And here is something that's a cool analogy for people who study physics, by the way. We have the graph network on one column, and an analogy of Newtonian mechanics on the other column. And for the scientists, it's pretty obvious because we have this input state, which are all these nodes, these particles at different state. Right now, I say state T0. And then you have pairs of nodes, which are two interacting particles. And then you have the edge model, which we talked about earlier, where it can compute the force. We don't know that it's computing the force, but it could be. And then you have all the messages where we want to encourage the sparsity here, because we're going to basically take a very sparse representation of the edge and approximate with the symbolic regression we talked about earlier. And we'll explain this a little bit more. And once we pull all these messages together, it's similar to summing over to the net force that each node is getting. and we concatenate with the node. In this case, sometimes your node have node attributes, say the mass and the current state, where it is at, the current position. And then you have the node model, which sometimes it could just take this total forces and divide it by the mass. But the network doesn't know these information, but it could be doing that. And you can update the node for computing next time step, and we compute and we compare to the observable, and then we update all the edges and all the numbers in the network. And hopefully when it trains well and outputs something that is very nice and very similar to the output that we expect, then we try to interpret it. Okay, so the outcome, here's the truth on the left, models on the right, just to show you that it is able to train and predict fairly well. And there's more outcome here. So it's the 1,000 steps rollout versus the truth on top, the predicting in the bottom. The boss bouncing in the four walls is actually surprisingly chaotic and actually doesn't do as well. It basically lost it very quickly, but the n-body system actually does pretty well. And 1,000-step rollout means, the first, we only train on one time step and we test on that one time step, but then we can't basically rolling it out for the dynamic system and see what happened for the next 1,000 time step after you learned the system for that one step. And we also did something called the zero-shot generalization to larger system, where you take the truth on top and the model, you can compare them, you can see, well, they're very similar, and you'll be like, okay, that's pretty good, right? But it is a system these are systems that the network hasn't seen actually. And the reason I said also see Lagrangian neural net and Hamiltonian neural net work is that I think it would be really interesting to improve the systems by adding basically the global properties using the Lagrangian or the Hamiltonian paradigm. So that's another part that we haven't talked about, but I encourage you guys to take a look at it, given the audience here probably scientifically inclined. So now I hope you understand and believe that the network does okay well in predicting the next step of these systems. So what do? We have one challenge left, which is to extract a symbolic equation. And as I mentioned earlier, we actually need to reduce the dimensionality of the edges messages. So when we record the messages here and from the edges, you want to really reduce the number of elements that are actually important. So there are many ways to do this. We end up doing L1 regularization, but actually, I think now we have a different project and we know that L1 regularization is not necessarily the best, but for this system, it worked okay. Given the input simulations 2D, we at first actually tried forcing the edge factor numbers to only be having 2 elements, not larger than 2. But when we limit it to 2, it immediately makes training much longer and the performance not as good. So we try actually a bunch of other regularization, and we settle into the L1 regularization to minimize the number of message elements that are important to fit the observables to the predictions. By the way, I just want to mention that this choice is particular to this, situation, this case study. We have done something completely different, which is using similar idea to predict very complex set of equations in turbulence simulations. And there, L1 regularization just doesn't cut it. We actually sort of invented a different way to sparsify this network. So that's a different story, which we won't be talking about today. And then we put the edge element through the symbolic regression package that Miles actually put together now. It's completely public, called PySir. Definitely look up Miles Kramer, and he has put everything public, and we can see what we fit for the 2 elements or a few elements that we have. And we found the force laws we recover from the systems, both for the springs mass system and one of our R-square law in 3D. So we were pretty happy. And then, usually you always get the referee asking you to do something much harder. So we were asked well, you seem to be only doing the easy cases. Can you do something harder, or at least something that we do not know the answer ahead of the time? So we did that, which is a simulation of a large scale structure of the universe. This is a cluster. and it's forming. It's at 3.4 billion years now, and it's very complex. The blue dot is actually the dark matter. For those who actually do cosmology, it's a bunch of our universe is formed by these particles that hopefully is particle called dark matter. And we think that it doesn't interact very much. It's cold, it's low temperature, it doesn't move super fast. And they interact only gravitationally. It's dark because we don't see it. And we now have all these explosions from supernova. So it's a complex simulations. We're running it from Illustris. So we take these simulations and we want to ask ourselves, for this such a complex situation, what is the central density of the clump here, right? The center of the dark matter halo. So what is the question here, which is a challenge, is that what's the density of the dark matter within the center of the dark matter halo, which is basically a cluster of galaxy, given the surrounding halos? So we can make guesses of what this answer may be like, but we really don't know what the analytical formula is from the previous work. And so this is a challenge because we have sort of very little idea what it should be. We have some guesses, but no one has tried to do this before. So let's try this. We try to find a density at the center of these dark matter halos. We have a detailed dark matter simulations that in this case, we didn't use the hydrodynamic simulations we showed before, but the dark matter simulations is sufficient because we're mostly thinking about the dark matter here. We have halos in the center. We want to find the central density. And we have all the surrounding halos. We actually encourage low dimensionality representation at the edges, just like what we did before. And we actually uncovered a dark matter overdensity equation that we don't know anything about, and we still are trying to interpret. So the result is we find a new analytical formula that can fit to the observable better than what we can fit using physical intuition that we sort of force ourselves to think about. These are the old, possible choices that we can think of. So we have constants, which is obviously not doing so well. We have a simple one that we think it would depend on the masses of the surrounding halo, and we let all these constants float, and it did okay. And now we ask network, like, can you do better? Best with mass, which is similar, which is comparable to this one, which is allowing the network to use mass. It has come up with an equation that is surprisingly different from what we've seen before and what we guessed before. We actually never really looked at what the formula that should be. And it does better in predicting the central density of these halos. So it does better as you observe. We can also force a network and say, hey, so if we don't observe masses of these halos at all, we just observe, say, the radial velocity. This is an observer perspective. If I can only see, the radial velocity of these galaxies in the cluster, we have some idea of the velocities, but really not the mass. So can I do it without mass? And the network came up with a different equation also, but it's somewhat related to this, not exactly. And it doesn't do as well as when you allow it to use mass. But both of these actually do better than our simple, intuitive formula that we came up with. But right now, we still don't know, why this formula, like we just haven't talked to enough theorists to figure out what the answer is. Right now, we have phenomenological equation that describe the observable better, describe the situation better, but we have no true understanding yet. And I think that's where the scientists should really come in and try to pull some understanding out of this. And then the next thing we did is, how about using some real data? So, but before I go on, can I ask if there's any questions? I'll pause here. Did I lose everybody? It is late for you guys. Jamie, go ahead, just unmute and say something.
This might be a naive question, but to what extent does this returned formula depend on specifics of your numerical simulation? So, I don't know, a choice of force softening or mass of the individual particles or things like this?
That's absolutely great question. We actually did not go and check everything because this is sort of, trying to do it the first time to see whether we can find a new analytical formula that we don't expect. But I do expect that it might depend somewhat on, maybe the simulations is wrong, or maybe the simulations chose to do a different, halo finder that might give you a different halo. But I suspect it'll be fairly consistent across, because dark matter simulation is pretty well understood. And we actually use one of those very high resolution dark matter simulations. Well, not very high resolution, high enough resolution that most people will be quite happy with the mass resolution for the halos. So I think this will be a good guidance towards, what these formulas should mean or can mean. But it could be fun to try to see whether it depends on the mass resolution or different choices of halo finders or different choices of integration scheme, all that stuff in general, when you find an equation like this from simulations. But yeah, it's a good question. And I saw some other question. People raised their hands. Seb?
Yeah, hi. So I just want to clarify. I think this is really, really cool stuff, but I'm going to play a little bit of a devil's advocate on you, if that's
Please.
all right. So in engineering, for instance, there are lots of sort of relations where they basically like assign power laws or something, which is just empirical, but it's always quite a useful way to be able to sort of estimate the properties of, I don't know, a pipe or a bridge or whatever. And I can't help but wonder whether the machine learning algorithm here is doing a kind of similar thing, where it's doing a very, very advanced fitting, which may be really useful to understand properties of the system, but may not be, as it were, physically realizable. So if you were to go to a theorist, they might just say, what you've got here is a really useful fitting, but not necessarily something realistic. And I just wondered what your comments would be to something like that.
Excellent question. Great question overall. I do totally agree with you. I do not claim that these are physical equations. I think these are, I can think of it as phenomenological fitting formula, that we have a way to describe the observable, but that doesn't mean that it is truly what's happening, right? So for the longest time, people thought Newton's law is correct also. And then, we realized that actually we should be using general relativity, but it wasn't obvious, because what you can fit and what we can observe actually fits well with Newton's law. So until then, I think there's always a question of going from, macroscopic fitting to microscopic. Can we understand it? We can probably fit something how muscles actually interact with, your arms and your legs. So we can probably get a fitting formula how they interact with each other for the robot, but we don't truly understand how molecularly what's going on there, because at some point we need to ask ourselves, what is useful. I think this will become useful as a guidance for the scientists to think about what's happening, but it might not give you understanding, and I don't claim to give you understanding, which is something that I think we still need the scientists for.
That's helpful, thank you.
Yeah, and I think Harry has his hand raised, and people should feel free to show your camera if you want, show your video.
Okay, can you hear me?
Yes, please, go ahead, Henry.
Okay, so I'm actually very interested in what you, in this research. I believe I read this paper a few months ago, and I saw, and I thought it was very interesting that you can derive, like an analytical over density formula from the environment like this. I'm curious. What so.
I think we lost you for 2 seconds.
How about now?
Yeah, better. Go ahead.
Okay, so.
We lost you again. Are they allowed to text?
I'll try posting this question in the chat. So
yeah, that would be great. Can you? Are you allowed to use chat? Yeah, I hope you can.
Yeah, sure. We got up to you were saying you were curious about something, Harry, then we lost it, unfortunately. So, let's see, we got it in the chat.
Yeah, and people should feel free to put questions in the chat if you don't want to say it too, or maybe connection's bad.
Is there any other questions whilst waiting for Harry to type in his question?
Yeah, any other questions? Feel free. In real person, usually I offered beer or coffee, depending on your preference for asking questions. But since we're not in person, I can't do that, unfortunately.
Yeah, it's one of the drawbacks of being on Zoom.
I know. But I do want to come to England soon. I have family in London now. Says my sister just moved there. So
Okay.
yes, question. I'm curious how you select the local halos to best derive the overdensity formula. What other properties could you derive analytically from your GNN? So in this case, we use the halos and surrounding halos, right? So in principle, I would also use the environment of the halo, where it sits. And this is kind of obvious. We did not do that just because we're responding to, just trying to see whether we can do the simplest thing, which is just using surrounding halos, because it's still somewhat reflective density, and see whether we can do that quickly. So that was why we tried that. But I'm sure if we put in, say, some kind of analytical or some kind of attributes for each of the halo in the center, what are the environment immediately around it, it will probably help. What other properties could you derive analytical for your GNN? I guess it depends what you want to do. You can also imagine finding the planet 9, like a missing planet in principle, right? So if it exists. So that's another possibility, which we haven't done, but I'm going to show you something that we have done later. Victor, you have a question. Go ahead. So thank you, Harry, for the question. That's great.
So I was wondering, what was the particle mass resolution of the simulations that you used to train the model, and what's the speed up compared to traditional methods?
What traditional method? You mean to derive the analytical formula?
Well, compared to the to run the numerical simulation.
We're not trying to speed up the simulations. The simulations were there so that we can try to find a new sort of understanding, hopefully some understanding, but at least a new analytical equation to describe these relationships. But we're not trying to speed up anything actually here. I usually have a speed up talk, like where I accelerate simulations, but this is not the case this time though.
Oh, okay, sorry, I misunderstood.
No worries. I have a accelerated simulation talk with ML, but this is not today. But we can talk about it another day though. All right, let me show you guys what I want to show you next, because I think it'll be really fun. Can I potentially derive radial profiles, merger rates, evolution details, or does it require more memory intensive environmental data? This is actually a great question. Also, we are doing something related using GraphNet to look at merger trees and how merger trees actually affect galaxy properties or halo properties at the end using graph network. So that's another project we're actually going on right now, and stay tuned, I guess. We'll see. We just started. So it's another project with a Princeton student, also with Miles, but another Princeton student called Christian Jasperson, who just arrived. But yeah, great questions, guys. And else, yeah. All right, next thing. How about using some real data, right? So all the stuff I've talked about used simulated data, and it seems super easy. So what we did is we take the NASA Horizons data that has, these things observe all the planetary bodies and the moons for over 30 years. So we took this and then we say, okay, let's try to do what we said, except that this time we use real data. We have the positions of these planetary bodies for the last 30 years. Okay, but they do have errors, but they're small errors. So we use actual orbits from 30 years of observations, and we did symbolic regression like we talked about before. First of all, we actually model it with a graphical network. So GN is a graphical network, given the distances as edges. So we also give it distances, and the nodes with the learnable scalar properties. So we don't know what the masses are, because these planets, we had no ideas from the orbit data. It's only orbital data right now, right? So we use this graphical network, basically compute the forces and all that. And it turned out that when you run the symbolic regression, you do get back to Newton's law, basically. And we also learn the scalar quantities. I'll show you. First of all, can we predict the interactions? So the left is the data from the bodies of the inner solar system. I'm sure we can plot better, but this is one of the plots we've made. And the right is the same bodies evolve from the same initial conditions, but use to learn interactions. And you can see that they're very, very similar, if not exactly. And one more thing is kind of cool is that we did derive all the masses of all the bodies that we've looked at. And I'm showing you the true masses versus the predicted masses. The true masses is mt over m sun. We take the log of it. So the stars are true masses. And the orange one is the predicted masses. And you can see that some of them don't do so well. Most of them do okay well, but some of them don't do as well. And you'd be like, okay, why? This thing doesn't work. So it turned out that everything that doesn't work so well is because it is a very minor perturbation on the system it is in. So like Mercury is going around the sun, but Mercury is really light, and so is Venus. So it's very hard to actually observe very easily, how does it perturb the orbits of these planetary bodies, because the major part is the sun. And then it's also similar in other cases where the moons are not doing so well because they're so light in the system that we had considered. But all the other ones actually seem to do very well within 10%. So we're very happy that even though some of them don't predict as well as you think, but it's for good reason, because physically, that it has very small perturbation on the orbital data. And one thing is that we do try to find GR, but it turned out that because the perturbation is so small, sorry about that. And the perturbation is so small that it is extremely hard to find, a difference from Newton's law, because it's just so small. And let me conclude. Human interactions and physical intuitions help us create new ways of thinking how to do machine learning. These new ways of doing machine learning, such as graph neural network, help us simulate what we see in the real world way faster. And what is more, I hope, intriguing, at least, or interesting, is that even for physical laws or phenomenological laws that we don't know the answer to, we can observe the system and let machine learning help us find analytical expression. And I'll stop here and I'll answer questions. Thank you, guys.
Thanks so much, Shirley. It's a great talk. So do we have any more questions for Shirley? You've got quite a few questions that went along. A few rounds of applause there, that's good.
People can also just type in if you don't want to raise hands. Oh,
Got a question
thank
from
you.
Carol.
Hi, Shirley. So
Hey, how are you?
I want to ask you a bit on more on your opinion on interpretability. So I guess one way of thinking of interpretability is looking at analytical equations like you do, right? But I feel like that might be a bit putting our biases as physicists in, right, of what something being interpretable mean. So I would just like to hear some thoughts from you on what you think about these things.
That's a hard question. I think interpretability, if you ask 5 people in a room, they all give you different answers. And so I sort of gave you my very biased answer, which is to have a formula if you can. And if you cannot, I guess very often people would like to perturb the input and see how it perturbs the output, which is, very old school, not old school, but classical method, looking at things like saliency map, which basically is looking at the changes of inputs how it affects the output. But I think interpretability is so wide. Like that word itself can mean so many things. I'm just going to stick with my small scientific bias answer here. Thank you.
Next we have Joaquin.
Yeah, thank you. Thanks for the talk, Shirley. It was really nice. I want to ask you about the cosmological simulation project. So you're using this very high resolution simulation, to learn about physics. But what if instead you use something like an emulator or more chip simulations, to have more an statistical significance of what you're trying to learn?
So we, in this particular, so I'm usually very much into, doing machine learned emulator and all that stuff to accelerate simulations. But usually I do that because I needed the numbers to do inference. I needed the speed to do inference, right? So for Joachin's question, it's very related to my other side of my research, which is if I want to do deep learning assisted simulation-based inference, where I can use deep learning to make it either the simulation part faster or the inference part easier because we explore such high dimensional space. And very often in scientific community, we have the situation where the simulation is basically our theory prediction. And a theory prediction has to be fast with very many background parameters, run through, whatever that is. It could be initial conditions choices. It could be, maybe what model we should be running for the universe. It could be what model we should be running for the supernova feedback. It could be all kinds of stuff. And that, if you can make it faster, then you can compare with the observable in a way that might be very high dimensional. And so there's another part where deep learning, I think, also comes to help is how to explore and basically do gradient descent or some kind of minimization or optimization very fast. It doesn't actually really mean deep learning, but maybe even machine learning. Traditional statistics also there too. So people can talk about HMC, can talk about variational inference. There's all these things, and I think that's where we wanted to have this emulator, this speed up. But in our case here, where I just want to derive an equation, we wanted to have enough data, but we have enough data. It turns out that it's not changing the answer if I give it another simulation. So we should check for convergence, but it's not about so much about I need 1,000 simulation or 10,000 situation. But that's a great question. And then I know you probably know my other work, which is why this question is very related to the other side, which I love to talk to you guys about.
Okay, thank you.
Very good. So next, I think, was Seb.
Yeah, sorry, I just think this is such a cool topic. So I think one of the things I was curious about, it's just a quick question. If a scientist wanted to apply your techniques and they had, let's say they had a guess that, oh, particles over here are very unlikely to affect particles here. Like the leading order effect will be, local, a bit like, gravitational maybe or something else. Could you add those biases into your simulation, and does it make it quicker? Does it converge faster, or does it actually worsen the quality of the predictions?
Yeah, so given that Durham actually runs this, they have actually really good cosmological simulation people who can probably answer that question much better than I do. I think their actual Carton might even know better than I do how they actually do this faster. From a very limited understanding, there are many methods that people have explored to how to figure out the fact that there's multi-scale physics interactions and how you exploit it to make the simulation faster. But I'm sure they're much better experts here than I am to answer that question.
Because I mean, the only reason I ask is because you can imagine if you've got like a complete graph, that's obviously a lot of, combinatorially that blows up quite quickly. But if you could sort of say a priori that, okay, these particles aren't going to affect each other, so my graph is going to be fewer connections, it might be faster to run the actual machine learning techniques. I just wondered whether you had any ideas about the biases there.
That one I do think I can answer. So for the machine learning side, if you think that it's actually very important to know how many edges you want. So you might not need a fully connected graph. And if you know that they're not talking to each other anyway, just don't do it. And then the other possibility is something that we're working on right now. I'm not even sure I'm allowed to talk too much about, but you can also coarsen the graph, which means, I think Carton and others who do simulations very familiar with the idea that, a particle here just need to know the broad, overall force from the other chunk of stuff over there. So there's a coarsening perspective that we can impart into the machine learning situation here, which we are doing. We're trying to say, these dynamic simulations, we're trying to do it so that Miles actually currently in an internship at DeepMind. They're trying to figure out how to coarsen it so that we don't need 100,000 nodes to model like water moving around, because you probably only have a few modes, right?
That's really cool. Thank you very much.
Good question.
So it's exactly as Shirley described, sort of aggregating very distant particles, so you don't need to know in detail where things are. And I think Thomas has had his hand up for quite a while, patiently.
Hey, yeah, thank you for the nice talk. I guess what I was thinking was how, like when it comes to actually implementing this, how disentangled are the machine learning systems and the environment you put it in? Because, for example, in like condensed matter or particle physics, loads of people try and find like critical exponents, which effectively these power law relations that you can get analytically. Like, how easily would it be to just apply that to a toy model from condensed matter or particle physics?
You have to say that again. I don't know the model in condensed matter and particle physics at all.
Well,
so
say
any details.
Any model you like, you have like, you think up a model, you think up a Lagrangian, you can do a simulation in like 2 or 3D space, and then you generate some simulations, and people like to like extract, basically like you're saying, like how much, like what is the power at which interactions depend on the distance between them, for example, like arbitrary fields and then arbitrary powers that relate those fields, sort of like how you extract the powers and of like the mass in the previous example for the gravitational. Like how hard would it be to take your model or your machine learning element and just apply it to a new simulation without knowing any of the underlying structure?
Yeah, I think it's pretty easy as long as you think that the underlying simulations that you're using works well with these nodes and edges. So like something I'm not 100% like, I wouldn't do it for, say, image recognition, because you basically have, convolutional neural network quite well, or sometimes people claim transformers work better. But I would not turn it into a scene graph, for example, right? But while here, if you're talking about like particles, interactions, stuff like that, that will be pretty easy, I think, to just take what we have and just run with it. So our network, someone from CCQ, like quantum people, are starting to use, for example, and they're in quantum. So they just like very small things that's happening, and it seems to be okay.
Great, thank you. Cheers.
Thank you. It's a great question.
Any last questions for Shirley? I think you've broken the record there for the most questions, certainly at any talk that I've seen this week. So you've got a huge number of questions there. That's really great.
Thank you so much for being such an interactive, awesome audience, especially over Zoom. I hope to see you guys in person sometimes.
Yeah, it might have to be next year. We'll have to see, but yeah.
I don't know. I'm probably coming to UK sooner than you think.
Oh, very good. Well, you should pop into Durham then if you've got a chance. Brilliant. Okay. Well, let's thank Shirley again, and that brings to an end this afternoon's talks. So we'll see you again in the morning for the careers panel and getting a few more rounds of applause there, Shirley, as well. So thanks very much, Shirley.
Thank you. Thank you, everybody.
Bye, everybody.
Thanks for being so patient.